I'm going to talk about the Doppler effect. I'm not going to get into heavy mathematics. I'm going to get into the concept here. Doppler effect is when a source, and really what I mean is a frequency source, and an observer are moving relative to each other. Okay, so if I'm standing over here and somebody else is standing over here and they yell, well, the sound waves move out, really 3 dimensions, as we'll see, and I perceive a certain frequency. Well, we've got speed, let's say 331 meters per second, let's say STP, speed of sound. So if this person emits a frequency of 440 hertz, something like that, then 331 would correspond to a wavelength. 331 divided by 440, V equals F lambda. So the wavelength is about 0.752 meters. So that means these things are 0.752 meters. The condensations are 0.752 meters apart, and the rarefactions are, and they're moving along, and they stay 0.752 meters apart. Over here, when that wavelength hits me, I say, oh, okay, well, since there's that speed of sound and that wavelength, V divided by that wavelength, I hear a frequency of 440 hertz. So as long as we're not moving relative to each other, I'm hearing the exact same frequency this person emits. Okay? But what happens if this person starts moving? Still emitting a 440 hertz frequency, but they're moving now. So let's think of this. A second ago, or a moment ago, they emitted this condensation. Then they moved. Condensation moved out that far. They moved here. And they emit another one. And this one moves a little further. But you can see the next condensation he emits is going to be closer to that one than he was. Think of it like this. If I have 2 balls and I'm on a car, I don't know, I'm on a bird, a scooter, and I roll one ball as I'm moving. Well, I'm going to be pretty close to that ball when I roll the second ball, if I roll them at even intervals. So the balls will get kind of be closer together than they would be if I just stood there and rolled one every second. Okay, so if I roll one and then a second later after I move, I roll another one, they're going to be closer together. So these waves get bunched up a little bit. Okay, so as this person moves with a certain velocity, and these are moving with the speed of sound, they get smaller wavelengths. So when they arrive at my ears, these smaller wavelengths, V equals F lambda, so the frequency I perceive is V divided by a smaller lambda, and that makes for a bigger, higher frequency. Similarly, if he's moving away from me, he's moving in this direction. Again, let's go back to the bird. If I'm on the bird scooter and I roll a ball and I'm traveling, and then a second later I roll another ball, those balls are going to be very far apart. This one was traveling here. I'm going back in this direction. I'm farther away when I roll that second one. So I'm spreading out that. So these wavelengths will be greater, will be longer. So what I'm going to hear is I'm going to hear a big wavelength corresponding to a very small frequency. Okay? And I'll show you some simulations on that in a moment. So here's what goes on with the Doppler effect. And by the way, this is from a site called thephysicsaviary.com. Has some excellent demos. Let's take a wave speed. Let's make it 100 meters per second. Let's take an object speed of 60 meters per second. And the frequency will keep at 1. As I start this, you can see what's happening is as this travels, the waves, you can think of the waves getting bunched up here. There's a smaller wavelength which corresponds to a higher frequency in front. So an observer out here would perceive a higher frequency. In fact, let's just do this. Let's do an object speed of 0. So this would look like if the object wasn't moving. The wavelengths here and the wavelengths here are identical. But as that object speed is higher, and let's go just 10 or 20, you can see the wavelengths here are a little bit shorter than the wavelengths back here. And once again, the speed of sound doesn't change. These waves are still moving through the air at the same rate, the same velocity. So if the wavelengths here are smaller, that means the frequency is higher. So you hear a higher note out here. Back here, you'd hear a lower note. Off to the side, it's really just about 100 meters. It's about the same. So it's not a moving object causes Doppler effect. It's moving relative to the observer. So here he's not really moving in or out. He's relative to an observer out here. He's just passing by. Okay, so if we look, let's go to 80 meters per second. And you can see it's really dramatically greater effect now. So these wavelengths are very small, correspond to a high frequency. These wavelengths are very long, correspond to a low frequency. So in this circumstance, what you find is, and also let's observe, these wavelengths are consistent. So when this velocity is constant, the observed frequency in front is constant. We increased the velocity, it definitely increases the perceived frequency in front of the object, but it's a constant increase, a constant change. If he sped up, then the perceived frequency would be constantly changing. But right now it's just a constant frequency that you perceive, and the same thing behind. Now, the same would happen if we had this person, this plane, sitting still. And let me turn down the wave speed just a bit. Okay, so if I start way off to the side and I start moving in, tick, 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 it's going to be very different from me moving away. Tick, tick. I'm even doing it faster than the speed of sound. I should slow down. Tick, tick. You can see that the frequency tick, as I move away from him, is lower. So when the source and the observer move apart from each other, there is a lower perceived frequency. When they get closer together, and it doesn't matter whether I'm the one who's moving, the observer is moving, or the object that's emitting the frequency is moving, the frequency is higher. The perceived frequency is higher. So the Doppler effect has to do when the source and the observer have relative motion. And it doesn't matter which one's moving. If they're getting closer, if they get closer with a certain velocity, perceived frequency higher than emitted frequency. Okay, so somebody over there is singing a 440 hertz note, boop, like that. If they start moving towards me, I will hear a higher note. Beep. I don't know how high it is. It depends on the velocity, and that's another thing. So if they get closer with the velocity, the observer will perceive, they'll hear a frequency that's higher than the emitted frequency, and the effect is greater if V is greater. relative velocity is greater. Okay? So if that person is just walking to me, let's say they're standing still and they make a note, boop. If they start walking towards me, that note, I will perceive a higher note, but it might be really small because walking is not very fast. So it might be, boop, might go up a teeny tiny bit. If they start running, it might be higher. If they're in a car coming towards me, it can be quite high. So that's why when we hear Doppler effect in real life, we hear, for example, a siren going by or a car horn going by. As the car horn's coming towards you, it has a higher frequency than emitted. So if they're driving towards me, I might hear a higher pitch, a higher frequency. And notice, it's greater if the velocity is greater. So if that car's going at a constant velocity, that frequency will be constant. It'll be a higher constant frequency. So that frequency that I'll call it observed frequency, right? Let's just say, that's the emitted frequency. If somebody starts a car, honks the horn, they're over there, and then they speed up, it's going to increase the intensity of that frequency difference that I hear. Then if they drive at a constant velocity, I will hear a constant higher frequency. Okay? Then if they slow down as they're coming towards me and slow to a stop, I would perceive that. If they then drove away from me, so constant velocity towards me, constant velocity away, would be like that. I would be perceiving a lower note. You see this all the time with cars honking their horns as they pass you. Okay? They're driving towards me at a constant velocity. There's a very, very, very quick transition. Then they're driving away from me with a constant velocity. Now, there's one thing I haven't talked about, and that's volume or loudness. As car is coming towards you, it's going to get louder. There is nothing in here about loudness. It's all about the frequency shift, the frequency difference. Okay, so Doppler effect does not have to do with loudness. Loudness is a function of it's physically closer. As it's getting closer, it's getting continually louder. So let me do a little better graph here of a car coming towards me. Car coming towards me, okay? And let's just do this. Frequency and loudness, volume, okay? As the car comes towards me, it's going to continually get louder. But if it's going at a constant velocity, the frequency will be higher than the emitted frequency, but it will be a constant higher number. So the way you break down these problems, if it's getting closer, the amplitude, the volume this will depend on where it is. Not how fast it's traveling, where it is, okay? Whereas the frequency will depend on how fast it's traveling. That's the Doppler effect. Doppler effect is a frequency shift based on the relative motion of an emitter and the observer. And by the way, if I move towards a still car, it's the same type of thing. If I'm moving at a constant velocity towards an object that's emitting a frequency, I will still perceive a higher frequency. So it's the relative motion. As they get closer together, the perceived frequency is higher. As they get farther apart, the perceived frequency is lower.